Understanding how to make a decision about a population parameter is very important, but more important these days is really how do we estimate population parameters. And gets us to a concept called a confidence interval. So a confidence interval is used to estimate it. But I want to talk about what does it mean to be that. So the whole idea is we have a value, we don't know what the parameter value is. We don't know what it is. We want to find out. So if we want to find out what that parameter value is, how do we go about doing that? And to do that, we need to do some kind of estimation. There are two types of estimations that exist. There is what we call point estimator and a confidence interval. A point estimator you've actually already seen. This is just some statistic that you calculate from the sample data. So like the population mean, you would actually get, give myself a little bit of space here. The symbol for population mean that we use is mu. That symbol there. We want to get that, for that we want to get what we call the population, the sample mean. So we actually use the sample mean as what we call the point estimator to find out what that is. So we're going to use we want to find out about the big population. To do that, we're going to find out about a little tiny sample. So we take our sample mean, the symbol for that is X bar. That's our point estimator. So the X bar, that sample mean, estimates what that population mean value is. For the population proportion, the symbol for that is just P. So we just have a P for that symbol. And then you use what we call the sample proportion. And the symbol for the sample proportion, because we're using P for the population proportion, we don't have a Greek letter, so we have P with a little hat on top of it. So in general, if we want to estimate any population parameter, and we can call it a certain symbol, we don't really need to. We can call it a symbol, let's say we call it, let's call it theta. So we want to find some parameter, and we're just using some symbol. You can do anything you want. You don't need to use a symbol at all. You just want to find some population value. We call it theta. Then we use that sample statistic, which we'd call theta with a hat on top of it. We like Greek letters only because we ran out of other letters. So if you want to find the population standard deviation, you use the sample standard deviation. If you want to find out the population variance, you use the sample variance. Want to find out the population median, you use the sample median. And that's just kind of the way that works. Point estimators are really easy to find. Most likely we've already found them already, but they have a few problems. One is that for larger samples, the estimate's better. For a smaller sample, the estimate's not as good. But when you look at the point estimator, you don't actually know what the sample size is. So you have no idea of how good that is based on the sample size. You also don't know how accurate your estimate is. And so we have to have some way of figuring out how accurate is our answer, not just the role of the sample size. And both of these problems are solved with what we call a confidence interval. So a confidence interval is where you have some interval surrounding your parameter. And that interval has a chance of being a true statement. In general, a confidence interval looks like, and I'll write it down what it looks like. In general, it looks like you've got some parameter, some statistic here that you're going to use. You're going to add and subtract some error amount. And that E, that theta hat, is that point estimator. Again, it could be the X bar, it could be the sample standard deviation. It's anything from the sample standard deviation. And that E is the margin of error. What are you actually adding or subtracting from both points? So it's known as the margin of error. We always see these when you talk about proportions. We say, the proportion is whatever number plus or minus 3%. So that 3% is that error, margin of error. And this makes an interval. The way we interpret them, and we're not going to talk about how to calculate them just yet. We're just going to talk about how they work and how we interpret them and what they actually mean. The statistical interpretation is that the confidence interval has a probability, and that probability is usually 1 minus alpha, though not always, where alpha is the complement of the confidence interval. So 1 minus alpha is what that confidence level would be. We usually call it C. So we'll say C is equal to, and I'm going to make that look like a 1 instead of some other weird letter here. So you have 1 minus alpha, and that just is your complement of containing that population parameter. In other words, you're going to have some value out there in the world, and you're trying to get an interval that captures it. So if you have a 95% confidence interval, then you would say that 95% confident that the interval, let's say we have an interval from 0.65 to 0.73, contains that true population proportion. That means that if you have 100 intervals, 95 of them will contain the true value of the proportion parameter, population proportion, and 5 will not. It's wrong to say that there's a 95% chance that that true value of the population proportion falls in there. We're not actually looking at the chances that's in that interval. We're looking at that interval capturing it. It's the parameter isn't moving around. It's a fixed number somewhere out in space, and you're just trying to capture it. And 5 times you won't, and 100 times you will. So you're going to throw a net. 95% of the time you're going to capture that net if you throw it 100 times, and 5% you won't capture it. And that's kind of what we're looking at. The real word interpretation is that depends on the situation. It's kind of hard to just write a general statement, but let's say I want to look at the percent of people who like vanilla ice cream, and my interval is 0.65 to 0.73. Then the real word interpretation would be that between 65% and 73% of people like vanilla ice cream. So that's what it would look like. I'm going to actually show you a little bit more about how we do this. We're going to actually go to this website and look at this. And we're going to do a few things with the website, but I want to give you a kind of an idea of what's happening here. So I'm going to get this website up. And the first thing I'm going to do is I'm actually going to go ahead and find out, and I'm just going to have, and we're going to look at, let's say, the weight of, let's do total cholesterol. And I'm actually going to not have an explanatory variable this time. So here's my values. I'm going to actually let n be all of them so I can get a value of that parameter. So this is every single solitary data value in here. It's not a sample. You can think of it as the population. It's not really, because it's not every single solitary person in the world, but it's pretty close. So we're going to go over here to stats, and we're going to look at what that mean value is. And it says the mean value is 3.9. So we have that mean value is 3.9. So we're going to come back over here to the data. I'm going to go into this thing called, it's kind of your app controls. We're going to show the confidence interval. I'm going to actually put in my null hypothesis of 3.9. And what it did was, you can see it actually puts that value right in here and then gives me a confidence interval. I'm going to change my n back down. I'm going to make my n to be, I don't know, let's do 50. And so now I can see, here's my confidence interval. Here's that mean. This is my population mean. So I don't normally know this. I'm going to do it in this case just to say I know it. Notice that my confidence interval captured it. I'm going to go ahead and compare. I'm going to go ahead and freeze that. So this is the one I'm comparing it with. And then I'm going to go ahead and take new samples. Take a new sample. Notice it still captures it. It still captures it. And if I do this a bunch of times, it's still capturing it. Sooner or later, one won't capture it, like this one didn't capture it. So I did this probably 10 times, and one time it didn't capture it. I can keep doing this, and it should be, because I have a 95% confidence interval, it should be that 95% of the time it doesn't capture it, and 5% it does. And what I mean by captured is, notice here's my interval, but my line's above my interval. If I were to change my percent, normally we have a 95%. If I were to just change it just to make life a little bit easier to 50%, then I can see a little bit better. I can go ahead and take my samples again. Notice again, if I did it 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and it looked like about half of those captured and about half of them didn't. So that's what we mean by capturing it. It's here, fixed out here in space somewhere. We're just trying to put an interval that gets around it. So that's what we mean when we talk about this. So the next thing I want to do is look at how the sample size and the confidence level actually affects that the width of the interval. So let's go back into this. I'm going to go ahead and look at this again. So over here, I'm going to go ahead and keep my sample size at the moment. We're going to go ahead and change my confidence level to back to 95. And I'm going to go ahead and show you what happens when I change my sample size. So I am going to go ahead and freeze this one again so I can compare it. Here's my sample size of 50, and this is how wide my interval is. If I change my sample size to, let's say, 500, now look, my interval is not nearly as wide. This was much wider than this one. It became much less wide. If I change it even to more than that, let's go to 1,000. Notice even narrower. If I go down to 5, well, let's do 10. If I do 10, notice it's really wide as opposed to this one. So as my sample size decreases, my width gets wider. As my sample size increased, my width got smaller. Again, I'll go back to the 500. Notice my width is really, really small compared to this one here. So I can see that when I have more data, I'd get a tighter interval. And that makes sense because you should have more, when you have more data, you should have a tighter interval. We're also going to look to see what happens when the confidence level is changed. So let's go back and look at that. So I'm going to I'll put this back at 100. And I'm going to go ahead and freeze this one. So again, I can compare. And this time I'm going to come over here to my controls. I'm going to change my confidence level to, let's go even more confident. So what we mean by more confident, I'm going to be 99% of the time, I'm going to capture that true value out there. And 1% of the time, I'm not. So notice here, 99% of the time, I'm going to capture it. Notice my interval got a little bit wider here. I'm going to go ahead and freeze that one. And I'm going to do this again. I'm going to make this much smaller. I'm going to do it 0.9. Notice it's not nearly as wide. It's much less. So only 90% of the time, I'm going to capture it. 10% I'm not. But when I'm more confident, then I have to have a wider interval. And the reason is because the only way I can capture it more often is if I had a wider interval to capture it with. So I get a bit less precision in my answer because I have a much wider interval. But here I'd have a much narrower interval, but I'm less confident that my answer is right. So if you want to have a more tighter interval, you might have to have less confidence than if you had a wider interval. And those are your two relationships we have here. A larger sample size makes the width of the interval narrower. This makes sense. Larger is closer to the true population. So the larger sample size you can get, the more narrow you can get. And then the higher your confidence level, you have a more wider interval because I'm more confident that my interval is going to capture that true value. So I need to have a wider interval to capture it. Think of it this way: if you're throwing hoops at things, if you want to be more confident, you're going to throw the hoop around a jar, let's say. If you had a big hoop, you're more confident you're going to get it. And so that's what it is you can be more confident you're going to capture that true value. You have to have a wider interval to capture it with. And those are the different things that are going on. And so we either have a wider interval and we get, we have a bigger sample size, we get a wider, your interval gets less, or you have more confidence and you have a wider interval. And of course, the opposite occurs with both of those. And so that's kind of what the basics of a hypothesis, of a confidence interval are. We'll get more into how to calculate them later, depends on the situation, but it's more of just understanding the basics behind them. So the more confident you are, the wider your interval has to be. The bigger your sample size is, the narrower interval you're going to have.